Hello, everyone. Today we're going to be talking about Lab 6 solution, and we're going to start from step 1. Just as always, we first need to install the packages. Uh, One way is just to simply select this one, and another way is to go to the packages, select install, and type the name of the packages that we're going to need. So we are going to need Tidyvers here today. Tidyvers, as we discussed earlier, is the package that we use for all of the statistical analysis, like used for data cleaning, analysis, visualization, and it's a collection of R packages like ggplot2, dplyr, readr, etc. So you can either install those one by one, for example, installing ggplot2 or dplyr separately, but Tidyverse includes all of that in one place. So give it a few seconds to be installed. Next, we are going to install this HMISC package. This package loads functions for data summarization, statistical analysis, and variable description. For example, when we want to use describe function, when we want to use cut2, etc. These are all in the HMISC package. And together, this Tidyverse and HMISC, they make R more powerful for handling, analyzing, and understanding the data. The next step is to load this package. So installation and loading are totally different. When we are installing the package using this function over here, it's like it goes to the repository of R, or it goes this accesses to the system servers, collects all the information inside those packages that we are installing. For example, all the coding that exists behind this one word of Tidyverse. It collects all of that and downloads it inside our environment in the memory that we are using over here. Okay. But loading, which we are using library command, is like we are activating and calling in that package. If we do not do this part, we will not be able to use the packages. We will not be able to do the analysis, even if we already have everything installed. So after installation, we need to run this part of the code, this code chunk, just to make sure that we have everything ready to move to the next step. So next, for all of the examples in this lab, you'll be using the same data, just as previous ones. We're going to be using Facebook data, but we will load it once in each separate step to ensure that files can be run independently and in any order. Okay, so you will see that we have this Facebook read.csv file run in each of these steps 1, 2, 3. So after I run this line over here, this code chunk, you will see that this new object is created in the environment named as Facebook, the exact name that I'm using over here. Okay, so let's see what we are going to do today in step 1. So we have attended an industry conference and learned a good target for average interactions per post is approximately 200 for a company with our reach. We want to know whether we are measuring up to this benchmark. So what we are gonna do, we're gonna try to test if our average interaction is more than uh, this approximate benchmark or less than or equal to it. And for that, we always start with preparing and cleaning the data. Um, and interactions is already created for us inside the Facebook data. It is already collected. So we're going to finish this chunk below to select just that variable and store it in an object called bench. So we are using this name for the object that we are going to create. And I'm not going to do the calculations on the Facebook data itself. So I'm just selecting the variables that I need, which is interactions here, and storing it in the new object. See, we do not have that object over here. So if I run the bench, run this code chunk, we will have this bench object being created in the environment. Next, we're gonna run the chunk below to look at a histogram of your interactions variable and decide whether you have any outliers you should remove. So write a sentence below in the white space that shows these interactions. Your text should be blank, explaining what you've learned from this histogram. Okay. So when I'm just typing something, explaining this, it's going to be black. For example, the histogram that I'm just creating over here. See, this part of the line is black and this part is green. When you use the symbol around your text, just like this, it will turn your text into green and means that this part is not going to be printed out in the PDF at the end when we are going to knit this into PDF. Okay. But whatever that you write here to be part of your explanation of the graph or explanation of your analysis, it will be in black and it will be printed and will be showed in the PDF file. Okay, so let's run this part of the code to see the histogram. Pause the video for a couple seconds and think about what you see here in this graph and how would you interpret this. Assuming that you pause it, the histogram shows that most posts have very few interactions, while a few posts have extremely high values. This suggests the data are right skewed and contain some outliers that may need to be removed or analyzed separately. See, we have these outliers at the right end of this graph that you may need to remove them or analyze them separately. So it won't affect the main analysis of this part of the data. And you need to just explain that part over here by typing your explanation. I'm leaving that part for you as a practice while you're preparing the code as well. So next, we're going to be filtering the observations. Based on your histogram above, make a judgment call about how you want to filter, store, and the observations and data in the new object or the same object. So that's all your own decision, but I'm going to use the same object, just keeping just one object, this bench. And then I'm going to write a sentence below this instruction stating my decision. Okay, you can just type here that why and how you decided to do this part of the analysis. For example, what I'm going to do, I'm going to use exactly the same bench object, and I'm going to filter the interactions to be less than 2000, because I see that on the right end there are some um, extremely large values in the observations of interactions that I need to filter it. I need to drop that from my analysis. And that is exactly what happens in this part of the code. We don't need to, we are going to skip slicing part. We don't need that because we are working on just one variable. And we don't need to use grouping or slicing the data. Next, um, the metric that we are comparing to is an average of um, average 200 interactions per post. So we need to estimate an average from our data, run the chunk below to see two methods of getting an average. So basically, these are exactly the same. These two codes will give me exactly same results, giving me exactly same calculations, but only that they are two different ways. So the DPLIVAR way is a bit verbose, the one that we are using here. This uses the summarize command from the DPLYR package, and it's a bit verbose, but the work we do now will train us to be capable of the more complex codes later. If we just practice this, it will prepare us for later analysis and later codes. So look at the mean you've estimated. If it were exact, what would it tell you about your company's performance with respect to the benchmark? And then write a sentence with your interaction, with your interpretation that starts with, based on this estimate, our company. So what you're gonna do is you're gonna complete this sentence over here, okay? And if I run this code, I will see two different ways of calculations that I used here. So this one is showing this analysis, this one shows this one, prints out this one. So basically you see they are doing exactly the same thing. Both of them are just calculating the average of variable interactions. Okay, here I'm referring to the data like this. Here I'm using base R syntax. Then I have the variable name, and then I'm asking R to calculate the mean. So basically, they are doing the same thing and giving me the same result, 212. But excuse me. Um, but you can use any of them. Okay. All right. Then comparing this 212 with the 200, you can compare the analysis, compare the performance of our company with the average interactions at the industry level. This is what we are doing. Okay. Actually, it shouldn't have been 212. The reason that I got that number was that I had not run this part of the code. I wrote the code, but I forgot to execute it. So after I run this, I can make sure that the outliers are removed, I can go back to line 44 to 47 to run the graph code to make sure that now my data doesn't have the outliers. So now that my data set does not have the outliers, running the mean calculation or the average calculation code part, you will see that actually the average interaction for our company's posts is about 195.88 or 196. And it seems to be less than the industry's average. So we want to check, we want to test if that difference between 195 and the this 200 um, posts or the benchmark is statistically significant. So that is what we are going to do. So we are let's make sure to complete these steps for the hypothesis testing. Use your study guide to fill in all of these steps one by one, steps 1, 2, 3, 4, 5, in the hypothesis testing process below, providing the code and the chunk for the test you've chosen. Then we're going to run the test and see the result to check if this 195 is statistically different from the benchmark. So what statistical story are we telling here? Let's say deviation of interactions from benchmark is something that we want to test. We want to test whether our company's average number of interactions per post is different from the industry benchmark of 200 interactions. What have we estimated and what do we think the conclusion is so far? From our sample, we estimated a mean of about 195.88 interactions per post, which seems slightly lower than the benchmark 200 interactions. This suggests our engagement might be below the benchmark, but it aligns closely with what would be expected for a company of our size and reach. In other words, our interaction level is in line with the standard benchmark for similar companies in our industry and scale, but we need a formal test to confirm this. We need to see if that 195 is close enough to 200 or extremely below 200. And we are going to do that with a t-test. And when we are using the t-test, we always refer to the variable using the base R syntax, which is always like this. We have the name of the object or name of the data set from this environment and name of the variable. You can always find the name of the variable and name of the object here in the environment just to check the spelling. Okay. Then the benchmark average is 200, and I'm asking R to test that for me. Looking at these results, so we have this t-statistic value, degree of freedom, p-value, we have confidence interval, and you have learned about all those details, these numbers in your statistics course. So you should be able to answer to these questions. What is the statistical interpretation of the test results? So here, if I want to first interpret the p-value, I can say that the p-value is 0.71, which is much greater than the common significance level of 0.05. So this indicates that there is not enough statistical evidence to reject the null hypothesis. In other words, the difference between the sample mean and the hypothesized mean of 200 is not statistically significant. Looking at the t-value, we can say that the t-value of negative 0.369 suggests that the sample mean is slightly below the hypothesized mean, but this deviation is not strong enough to be considered significant when you compare this calculated t-statistics with the values in the t-table. Confidence interval here in this line, in this part, 95% confidence interval for the sample mean is between 174 and 217, 218, let's say. So since this interval includes the hypothesized mean of 200, it further supports the conclusion that the sample mean is not significantly different from 200. So this all includes lots of numbers, lots of statistical jargon like p-value, t-test, confidence interval, etc. But we also need to simplify it in the language of a non-technical people. So what is the practical interpretation or business interpretation of your analysis for the business audience? Note that your test gives you the confidence interval too. So we're going to use that or the p-value to interpret the results to justify the conclusion that we are going to give to our business audience. Given the p-value that we got, 0.71, we fail to reject the null hypothesis. This means that there is no strong evidence to suggest that the average number of interactions differs significantly from 200. For the business, this indicates that the current average interactions align closely with the expectations and benchmark. Therefore, any strategic changes or business decisions based on the assumption that the interaction level is near 200 remain valid. In practical terms, the business can proceed with confidence that its average interactions are consistent with what was expected or standard for their scale and their reach. But the confidence interval is wide. You see, we have 107 at the as the lower bound and 174 as the lower bound and 217 for the upper bound. And this is pretty wide confidence interval, which means our estimate isn't very precise. To get a clear picture of whether we are actually above our goal for interactions rather than just close, we should consider collecting more data. Okay, let's move on to step 2, which is going to be another type of the test, another research question, but we're going to follow exactly same steps as before. We're going to define our story. We're going to prepare our data by filtering, selecting, creating, and slicing. Then we are going to estimate our metrics, and then we're going to test our analysis. And if we want, we can always use visualization to just visualization or using other tests to confirm our initial results, our results that we have done earlier. So let's follow the same steps, but this time we're going to be comparing our paid and unpaid posts. Make sure to run this two first code chunks just to make sure that we have the data set ready and we have the codes loaded so we can work with them. Here's our goal statement. This time with a question to motivate it. Are we getting our, so we always have these stories based on the motivations, what our motivation is. Are we getting our money's worth when we pay for posts? This encourages us to test and to see if our engagement ratio is higher for paid than unpaid posts, which will lead to making a decision, okay, after we just complete the test. So the code below applies names to the values 0 and 1 for paid variable to make our tables and graphs easier to understand later. As you remember, for example, in Excel labs or Tableau labs, we used to, for example, in Excel, we used to use a VLOOKUP function. Or in a Tableau, we used different ways, for example, alias to replace these values with the numbers with their names and values. And this is how we do that inside R in R. And it will be helpful for us if we have the names shown or printed in our graphs, tables, and etc. It will be easier to read rather than having 0 and 1. Next, we need to create an engagement ratio variable. Use mutate to do this and name it engagement ratio. And the formula is engaged users divided by reach, and that's what we are going to do. Select these this variable and paid, and store them in a new object called paid unpaid. Okay, so this is the object that is going to be created this time in our environment after we define the names of each category, including paid, unpaid, and missing. Then we're gonna generate this new variable engagement ratio using engaged users divided by reach. And then I'm going to select engagement ratio and paid variable. Running this is gonna create this paid unpaid object. Here, this case when, which includes all of these stuff inside it, comes from the dplyr package in the Tidyvers. It lets you create new variables based on multiple conditions, a kind of like an if else chain in the plain language. The pattern is case when, condition 1. This is a condition 1, result 1. So it says that if this happens, do this. If this happens, do this. Okay, if this happens, do this. Right? It gives you the results. So it means that if paid is 0, it becomes unpaid. If paid is 1, it becomes paid. And if it's something else or missing, it becomes missing. Okay. Next, we're gonna be creating a histogram for each of those categories to see the details of the data. Run the code chunk below to see histogram of your new engagement ratio metric by paid and unpaid posts. Then write 1 to 2 sentences interpreting what you see and commenting on any outliers you think should be excluded. So the code that I have provided here is complete. You don't need to change anything. We have the ggplot command over here. The type of the graph that we're going to have is histogram, and we're going to have face wrap to have the histograms categorized or grouped differently for each of the categories of paid variable. For example, we will have one separate histogram for missing observation, one separate histogram for paid, and one separate one for the unpaid. Looking at these 3 graphs, we definitely do not need the missing observations. We're gonna remove that part, drop the missing parts, and then there are some outliers in the unpaid category. So we're gonna also filter that out. So in the next step, we're gonna just get rid of that. So let's get rid of the missing observations. You decide where to draw the line of outliers. You can decide to be, for example, 0.5 or 0.4. That's your decision. You can modify the code here to just reflect your decision and state your decision in white space, explaining what you did and why you did it. Okay. For example, I want to remove all of these extremely large values after 0.4, so I'm selecting this, and I'm only keeping the paid and unpaid category, and this will just filter out, this will remove the missing category in the dataset. If I run this, I will have that applied, that filter being applied on my data set. This time we do have groups, not just like step one. In step one, we did not have a group. We were just working on the interactions, but here we have a group and we want to just split the observations into two categories of paid, unpaid that are defined in the paid variable. So if I run this code, I will get that slicing part. My observations will be grouped by paid variable. I will have two different categories inside my data set. But in this step, we'll see the group by the work to convince yourself. So you can run the chunk above one by one in order, but skip the slice step. If you want to just check it, you can run the codes before this first. Okay, before this line, you can run all of these first and just run this code chunk over here in estimate. Then you will see, you can compare the result of that with what we are going to see now. Okay, in which we have run the group by. So look at your average engagement ratios, explain what they mean for your company's use. Use of paid posts if you take them literally. Okay, if you just accept these results of this part of the code, what will be the decision of our company? Although these are just simple averages and we haven't tested them statistically yet. But looking at these two numbers, we see that unpaid posts on average have a slightly higher engagement ratio than paid posts. Taken literally, this suggests that paying to promote posts does not necessarily increase engagement. And unpaid content may actually perform a bit better in reaching and engaging the audience. Next, we're gonna complete the hypothesis testing steps. Use your study guide to fill in the steps in the hypothesis testing process below and providing the code in the chunk for the test you've chosen. So then we're going to run that test. What is the statistical story that we are telling here? The statistical story is about determining whether the money spent on paid posts leads to higher engagement compared to unpaid posts. We want to test whether there is a significant difference in the average engagement ratio between paid and unpaid posts. What have we estimated and what do we think the conclusion is so far? So what we have estimated, we estimated mean engagement ratio for paid posts and unpaid posts. The average engagement ratio for the observations marked as paid, which is 0.108, and the mean engagement ratio for unpaid posts, the average engagement ratio for the observations marked as unpaid is 0.125. So, conclusion so far is that the initial conclusion from this analysis is that the unpaid posts have a slightly higher mean engagement ratio compared to paid ones. This suggests that this suggests that the unpaid post on average may be more effective at engaging their target audience compared to paid ones. However, further statistical analysis and context might be needed to draw firm conclusions. This is just simply based on metric calculations about, we need to just draw the firm conclusion about the significance or implications of this difference using a statistical test. So which test we will run? We will run an independent two-sample t-test because we are comparing the means of a numeric variable, in this case engagement ratio, between two independent and separate groups, in this case paid and unpaid categories. So we're going to use t-test and we're going to feed in the engagement ratio tilde paid using data paid unpaid. So you will see the result of the t-test here, the t-value, p-value, degree of freedom, confidence interval. What is the statistical interpretation of the results? The p-value is 0.02055, and it is less than the 5% significance level, so we reject the null hypothesis. This means that there is a statistically significant difference between the average engagement ratio of paid and unpaid posts. The 95% confidence interval for the difference in mean, these numbers over here, also confirm the same thing, does not include zero, confirming that the difference between these two averages, these two numbers, is real. Since the mean engagement ratio is higher for unpaid posts than the paid posts, unpaid posts achieve significantly greater engagement on average. The statistical analysis suggests that there is enough evidence to conclude that the engagement ratio for unpaid campaigns is significantly higher than that for paid campaigns. So the difference in means and the averages is statistically significant, with the unpaid group having a higher average engagement ratio. So this includes lots of statistical jargon, what we just said, talking about the p-value, confidence interval, etc. Next, we want to see what is the practical application and interpretation of these results, how we can just interpret this practically. So the relative narrow confidence interval, looking at this number over here, is relatively narrow. It implies that the observed difference between the engagement ratios of paid and unpaid posts is estimated with a good degree of precision. The sample size used in this analysis was significant to provide this level of precision, as indicated by the confidence intervals width. This adds credibility to our conclusion that unpaid posts have a higher engagement ratio than paid posts. Beyond mere statistical significance, the analysis of the engagement ratios between paid and unpaid posts provides valuable insights for business decision. So, how do we use this information for business? From business perspective, these results suggest that paying to promote posts does not improve engagement. In fact, unpaid posts perform slightly better. Although the difference is small, it is statistically meaningful, indicating that The organic content may naturally resonate more with the audience. So the company could consider shifting focus from paid promotion to optimizing unpaid or organic content, as this approach yields stronger engagement without additional cost. Um, in another word, for business aiming to increase engagement, emphasizing unpaid posts could be more effective. Okay, so make sure to complete these 5 questions, answer to these 5 questions in your own words. This should be number 4. Uh, okay, so visualization. Let's talk about visualizing what we got so far. So here is a visual summary of your analysis using confidence intervals rather than the test. And try to write up a 1 to 2 sentence explanation of the graph that we're gonna get in here. You don't need to make any changes in this part of the code, and if you run it, you will get 2 columns for the paid and unpaid categories with the um, error bars, and you see that the error bars are not um, just matching to each other. So one thing to add here is that you see there are 2 boxes in here, and in the first box you see a warning sign, and if you dig deeper on this might happen in the real world when you are working, because the codes are improving, the softwares are changing, and this might happen in real life. This is just a class. So what you're gonna do, you can always just look up the details of the warnings that you get inside the R environment. But here in this class, I can just explain what it is. In older versions, you could write this geom bar and having this function y on y equals to the mean. But now ggplot2 uses a new syntax with fun instead of fun y. So we're gonna use fun equal to this function equal to mean, or you can even remove this and writing like this. Both will work, either inside these quotes, double quotes, or just outside it. Both will work, and you will get the same result without that warning sign. See, you get the same graph over here, and this time you do not have the warning anymore. Okay, so as we discussed earlier, we saw the histogram and the initial steps for the step 2 that didn't really look like nice normal distribution. Let me just scroll up and show those graphs. See, these doesn't look like a normal distribution. This one is more skewed. This one has 2 modes for it. So when we do not have a normal like distribution, we're going to check our conclusions by comparing medians rather than the averages. So we're going to add a code below to estimate the medians of our engagement ratio by paid and unpaid posts. We're going to repeat the same steps as we did for testing the mean, but this time we're going to testing the median. And in your own words, explain why we are doing this. Double check of our results and interpret the estimated median. So we're gonna have, so we're checking the medians because our histogram showed that the engagement data are skewed and not perfectly normal. So I'm gonna use paid unpaid data. And you summarize at the first step, we are calculating the our metrics, engagement ratio, and I'm going to use median verb to calculate the median of engagement. Running this, is going to give me the median for each of these categories. And you see they are very similar to the results of calculating the averages. Next, we want to test if the difference between these two numbers is statistically significant. Because the data are skewed, we will use a Wilcoxon rank sum test instead of a t-test. So let's use Wilcoxon rank sum test, and we're gonna have engagement ratio tilde paid using the data set paid unpaid. And if you run this, you will get the p-value and Wilcoxon's statistic. So what you see here, the p-value, which is 0.04 roughly, shows a significant difference in engagement medians. Unpaid posts have higher engagement, supporting the same finding as before when we did a test for the analysis of averages. Okay, so our results does not change, and we can use the same interpretation, business interpretation, as we did before. Next, let's move on to step 3 with another analysis, another research question, another story, and a new test statistic that we are going to learn. Okay, we're going to analyze the distribution of posts across days of the week. So make sure to run this package loading part and dataset loading part. So here is our goal again with a question. Do we post more often on some days than others? We're going to use this question to, so this question motivates us to test the pattern. Let's find out whether the differences are large enough to conclude that we have a systematic pattern. So the first step is always to select the variables that we are going to need. So I'm going to use the Facebook data, and I'm gonna select weekday. Then I'm gonna run this to get this post patterns data set over here. Weekday is an ordinal scale variable, and we want R to know what order to put the values in. So that's why we have this information over here. And when we run the code chunk here to give R this information, it will just understand, it will learn the orders in the days of the week. If we don't do this, our tables will be out of order and confusing to read. To see what I mean, you can just go ahead and run all of the chunks after this point. And when you finish this, and then you can compare it with the results when you run this code, okay? You can compare the results of the tables to see what the difference is like. This level equals C is part of our language, and it's used when you define or reorder factors, categorical variables. And this factor function over here tells R that weekday is a categorical variable, not numeric. And level C after that defines the order. So we first tell R that weekday is a factor variable, is a categorical variable, then I'm telling that my categorical variable also has orders inside it, that you should just sort everything based on this order that I'm giving inside the level C. So the reason is that we are doing this is that weekday has that order, but sometimes some factor variables do not have that, so we do not need to necessarily do this part. For example, if instead of weekday we used post types being videos, photos, and etc., those do not have any orders in them. So we don't need level C for the type variable, but for weekday, we do need it. Okay, because we need R to know that my categorical variable has an inherent order, and it should be sorted. Or, for example, some other example could be Likert scale survey questions. Again, we have strongly disagree to strongly agree or whatever. This is also another example that we might need this arrangement over here. So make sure to run this part of the code. And then we're going to slice or group by the data set. So I'm going to use post patterns data, and I'm going to have group by command based on weekday variable. If you run this, you will have your observations being grouped by each category of group by. For example, you will have one category for Sunday, one category for Monday, and for each of these weekdays. Then we're gonna calculate our metric that we want to test. We need to count up the number of posts by day. This is like a pivot table in R, where we put weekday in rows and any variable we wish in the values box and change the aggregation to count. So run the code chunk below to see two ways of getting these counts, and then write a sentence explaining what these counts imply about our posting patterns. Does it look like we systematically post more on some days than others? And then we're going to check, we're going to test it statistically if it is actually systematic or if it is totally normal, random. Okay, we're going to check that later, but first we need to calculate the count the number of the posts per day and finding the metric first. Both of these are calculating the same value, the same metric, counting up the number of posts by day. So these are two different ways. This uses the dplyr package from Tidyvers package. So this dplyr package is a package inside the Tidyvers. And the other one uses the base R syntax. So if I run it, you will see that there are two boxes over here, and each of them relate to one of these. So this one is for post this tally option, and the second one is for using the table option, using the base R syntax. And looking at these information, pause the video for a few seconds and think about the patterns that you might see here. Looking at these numbers, it seems that weekends have higher number of the posts compared to the weekdays, but we need to check it statistically to see if that difference between Sunday, Saturday, and the other days is systematic or just a random distribution. So use your study guide to fill in the steps in the hypothesis testing process below, providing the code in the chunk for the test you've chosen. And then we're going to run the test and interpret it. These steps are always the same. We always follow exactly the same steps for hypothesis testing. So what statistical story are we telling here? We want to test whether our company posts equally often across all days of the week, or if some days receive significantly more posts than others. The data tells a story of strategic content distribution throughout the weekdays with a focus on higher activity on weekends or relatively consistent posting on weekdays with a slight dip midweek. So this is what we saw here, and that's what we want to test. What have we estimated, and what do we think? The conclusion is so far from the counts in this table, we saw that Sunday and Saturday have the most posts, while Wednesday has the fewest. And this suggests that posting is not evenly distributed, but we need a statistical test to confirm that. This pattern might indicate that the weekends are seen as prime days for content distribution, potentially due to higher user engagement or availability. Which test should we run? We will run a chi-square test, and we will feed in the table, the R syntax, the base R syntax for our data set, post patterns, and weekday. We run this chi-square goodness of fit test to see if the observed posting frequencies differ significantly from an equal distribution across all 7 days. And the chi-square goodness of fit test is ideal for checking if the number of posts on each day of the week matches an expected distribution. Okay. What is the statistical interpretation of these results? The chi-square statistic is 4.476 with a p-value of 0.6125, and which is much greater than 5% common level of significance. Therefore, we fail to reject the null hypothesis. This means that there is no statistically significant difference in the number of posts across the days of the week. In other words, the variation we see in counts, like slightly more posts on weekends compared to weekdays, is small enough that it could have occurred by random chance. It's not very large to like this for this statistical test to show it being significant. It's totally a random behavior. What is the practical interpretation of this from a business perspective? This means our company's posting activity is fairly balanced across the week. While there are minor differences in posting frequencies, for example, slightly more posts on weekends, these differences are not large enough to be meaningful or systematic. Practically, this suggests that the company does not have a strong day of the week posting bias, and posting is distributed relatively evenly throughout the week. And content creators or businesses should take note that their current posting strategy does not show a strong day specific preference or pattern. And if they want to show that preference or pattern, they might need to change that pattern. For example, if they want to focus on weekends and weekdays, they should post more than what they are doing right now. Okay. So we are done with lab 6. To prepare the submission document for this lab, go to master report. Make sure to change your name here. You can also fix the date. And you don't need to change anything here. As I explained earlier, uh, this part of the code is just combining all the steps 1, 2, 3. This code considers step 1 RMD file, step 2 RMD file, and a step 3 RMD file as the children of this master file. So these child files are going to be merged together. And this neat command, this neat part over here, after I run this neat to PDF, it will just combine all of those actions, all of those steps together and give me one PDF. So I'm going to neat it in the PDF. And you will have this PDF ready. If you don't see this pop-up viewer for PDF, that's okay, that's totally fine. Your PDF will be created here, master report PDF, and you will have all of your work and created, generated inside the PDF, including step 1, step 2, and step 3 with all the details of each step. And this PDF, this master PDF is something that you need to download and upload it. For example, I'm gonna say lab 6, Sarna's Babari, and then I'm gonna go to lab 6, start assignment, and then you can just drag and drop this file over here. It will be uploaded and then you can submit the file. Okay, good luck.